Hello, everyone. Welcome to today's webinar. I'm Jeff Huber, contributing editor at Chemical and Engineering News, and I will be moderating today's event. This webinar is titled Accelerating Consumer Products Reformulation with Machine Learning and is being sponsored by nThought. CNN works with sponsors to identify topics of interest and value to CNN's audience and consistent with CNN's mission to provide news and analysis of the chemistry enterprise in a timely, accurate, and balanced fashion. During the webinar, you can adjust the size of the slides on your screen by grabbing the lower right corner with your mouse. If you need technical assistance, please look at the Help widget at the bottom of the screen or type your query into the Q&A box. If you are disconnected during the webcast, please log in again according to the instructions you received earlier. You are encouraged to contribute to the success of this webinar by asking questions at any time during the presentation through the Q&A box on your screen. The questions will be answered at the end of the presentation, and as your moderator, I'll be posing as many as time permits. Please note that CNN does not endorse any company, products, or services that may be mentioned in the webinars, and that each webinar will be archived at CNN online after the live webcast. The presentation today is being sponsored by nThought. nThought collaborates with clients on their digital transformation initiatives to create opportunities that enable faster discovery and continuous innovation. nThought is fluent in the language of science and passionate about solving the toughest challenges. And with that, I will now hand things over to our first speaker, Dr. Farrow.
Thank you. And thank you for attending the webinar today. A little bit about me. I'm Chris Farrow. I am the head of the Material Science Solutions Group here at nThought. I'll be giving you the introduction and talking to you a little about what to expect today. First, a little bit more about nThought. We work with science-driven companies to accelerate R&D by building their digital capability. The approach that we bring to problems combines skill development through science-focused technical training, value-based software and technology development for scientific challenges, digital advisory ranging from digital strategy, inception of those value-based projects, cultural change, and we wrap it up with our scientific expertise, which allows us to deliver value in ways and work on problems that others really can't. We're bringing this approach to the problem of consumer products reformulation and talking about that with you today. Now, reformulation is one of the major use cases for machine learning in this industry and other materials industries. Machine learning in general is becoming widely used across materials and chemistry, but the innovation is still rapidly changing and it's far from over. Our approach is to bring up the skills and tool use within the clients that we work with, and our feeling and our case for today is that you or the people you work with or your company also needs these skills and needs to have the knowledge to be able to continue to innovate. We see programming, machine learning, AI, data management. These are all natural extensions to the modern scientist toolkits and ones that can greatly enhance what you do personally, what you can do within a group, and what your company can achieve. We're hoping to help you understand today how you might make use of these technologies in your own work. So, learning objectives. We're going to be talking about the specific use of tools and how you set up machine learning pipelines for the problem of reformulation. We'll go into some of the data concerns that you'll have if you're just getting started out with this. And again, we're hoping to convince you that you'll understand why it's important, why your company needs skills like this to innovate. In just a moment, I'll be showing you a video from our collaborator, Pat Spicer. It's 2 a.m. for him right now, so we recorded his portion. And then I'll hand it over to Mike Hyber, my colleague, and he's going to be the one who provides the example, going into the details, showing you specifically, telling you what you need to be concerned about when it comes to data, and how to set up a machine learning pipeline for your problem so that, again, by the end, you have a sense of how to get started on these problems. Even if you've already done problems like this and you're getting started, I believe you'll learn something, so please stick around. But with that, I'll show you the video from Pat. Thank you.
Hi, I'm Pat Spicer. I'm going to be introducing the topic for today, reformulation and development in the consumer product space, with the focus on how machine learning can help with that. Is something that I've been working on with nThought for some time, and it informs a lot of the research that I do as well. So my background is chemical engineering. I was trained in the field of aerosols and particle technology. And after my PhD, I went to work for the Procter & Gamble company, where I worked for most of my career in their corporate engineering division. And in making that transition, I had to learn quite a bit about new areas like the formulated product space, how consumer products take a number of ingredients and develop the properties that consumers want, but also how they deal with scale up and product and process development in that area. And that was the focus of my group's work for the 15 years that I worked at P&G. Now I'm a professor in chemical engineering at the University of New South Wales, and I focus on really research into materials very much like what P&G used to develop a lot of their commercial systems, and that's complex fluids. These are used in pharmaceuticals, consumer products, foods, all sorts of systems where many ingredients come together to have a lot of attributes. And so today I want to introduce the topic we're going to be talking about. So there are a lot of challenges in complex material development. You know, whether you're dealing with solid or fluid forms of formulated materials, they can be deceptively complex. Even though we see these products every day, we can not necessarily see through to the complexity that underlies making them successfully on a large scale. One of the key attributes of materials like this is that instead of commodity chemicals and materials like that, where there's a focus on purity and compositional determination, for formulated systems, what you wind up having is a focus on very different histories or levels of treatment, so much so that you can actually have identically formulated materials behave differently if they've been processed in a different way or they've had a different history. So this is a real issue, and nowhere is this more true than in the formulated products sector. You know, one surprisingly difficult process is making a stable emulsion, for example, where you mix two liquids and you wind up with a bunch of droplets suspended in the other phase. And if you have a high internal liquid phase, this can be surprisingly hard to make stably and reproducibly. Anybody who's tried to make a homemade mayonnaise has encountered this kind of system. And concentrated emulsions are also equally useful in things like cosmetics and pharmaceuticals. And so if you take the liquid ingredients that go into these emulsions and you don't prepare them in the right order or at the correct rate, you wind up with a system that is not an emulsion and is not stable. And this is annoying on the kitchen scale, but on a large manufacturing scale, it can cost you money and time and far worse. And so to do something like this really reproducibly requires long experience and deep understanding to get it right every time. But that kind of knowledge is often not documented or widely known or shared because it often resides with the few senior people who have seen this before. And so these kinds of multifaceted problems come up all the time in consumer products and other industries. And, you know, they can even affect the product behavior over long periods of time. One system that we faced like that was a product that required suspending microcapsules that contained oils. And what this required for the product was that these beads or capsules be stabilized and suspended for months, basically the shelf life of the product. After doing testing, this was found to be fine. For static studies, no difficulties were observed. But then when the product was transported by truck to stores, and it went over bumpy roads, when the product arrived, all of the capsules had settled out and the product was basically a failure. But the interesting thing about this was that failure of performance and aesthetics wasn't observed for products that were transported by ship and had a relatively calm ride. And so the models that we had for these systems really didn't predict this sort of behavior, and only experienced technologists were able to make the connection and find a fix for this product formulation. And this comes about, as I say in the slide here, because flow properties for complex fluids are very hard to predict, and they really must be measured in many ways to understand the performance. And this slows you down, but it also generates large volumes of data. And so this can happen over product development cycles and over companies' development histories. And it really creates some unique needs for the companies who develop complex fluids. So as a result, there really is a need for understanding these sorts of products in a new way, because consumers want novelty. They want new products in relatively short timescales. And, an example of this is the demand for reformulating products to be more sustainable, or to remove ingredients that are no longer permissible or favorable to what people actually want to see in products. And so this creates a demand for product technologists, for product developers and formulators. And even when people do have the expertise to do this type of work, having access to that expertise is not always uniform. Companies that expand hire new and mid-level technologists, and they really need access to this kind of institutional memory and in-house expertise in order to deliver the rapid development that people are looking for and really keep pace with the kind of continuous changes that we're seeing in the product space. And so as a result of this, companies are really under pressure to maximize the applicability of historical data that they have, to broadly share some of the expertise that's out there, and to really provide guidance to the new people that come into play. And so what we're going to be talking about today is the topic of really using machine learning to aid in these kinds of reformulation and development efforts. And they'll be giving you some specific case studies and, really talking to you about how digital transformation can aid in the materials and formulated development work in the product space. And so using this, it's really hoped that you'll find ways to speed product and material development, and especially help enhance data-driven decisions in research, because nobody wants to have data that they aren't able to use and reapply in a nimble and efficient way. And that's going to be one of the biggest areas we're going to focus on today. So as I said, I'm working with nthought to try and target some of this into the space of the consumer product industry. And today you're going to be hearing from experts in this area around their unique approaches to helping aid materials and product development work, enhance the speed at which new developments can occur in your company, and really help you make better decisions with the data that you have. And so I hope the presentation today sparks some ideas for you and makes connections where you didn't previously see them, and makes these ideas accessible and enables you to see where these sorts of things might be applied. Enjoy.
All right. Thanks, Pat, via video. But hi, everyone. My name is Mike Hyber. I'm going to be presenting the next section. Just as a brief introduction to who I am, I'm a polymer scientist by training. I have a PhD from the University of Akron studying polymer science. And after leaving there, I had an extended academic career where I was really pushing myself to learn new digital skills and technologies and apply these to my research. And I have continued doing that in my work at nthought. And so I've seen firsthand through my own work, through my colleagues' work, and through my clients' and our clients' work, how digital tools can really accelerate and improve the research that we do in the lab. And at nthought, I've continued expanding on this and making sure that we're able to apply these digital skills and tools to business problems that have real impact. And so today I'm going to walk through an illustrative example of how digital tools like machine learning can be used to tackle materials and chemical product development problems through a specific industry-relevant example in the personal care products industry. This project was largely executed by a great team of interns under my supervision at nthought over this past summer, in collaboration with Professor Roger Bonacase at UT Austin, who we're also working with. So in this scenario, let's say that I'm a product development leader at Acme Corporation in the personal care products division. Our business develops and sells a variety of products, including hand creams, body lotions, skin ointments, etc. In recent years, customers have been demanding greener, more environmentally friendly products with sustainable natural ingredients. And we've identified an opportunity for a new product line using natural ingredients that have recently come onto the market that leverages one of our existing technology platforms. So the big question is, how can we rapidly reformulate our existing product line to target a new high-value market segment and make sure that we beat our competitors to market with our product? Of course, there's a lot involved in bringing a product to market, and I'm going to focus really on the R&D side of this to reach the point where you can hand this off to product marketing and product sales side of the company. But here are some sort of qualitative product specifications that one might get from the product marketing side. Right? The product needs to stay in the container when it's not being used. If I simply open the container, the product should not ooze out. Or if I scoop or squirt some product into my hand, it should not immediately flow through my fingers. However, at the same time, the product must easily spread on my skin as I rub my hands together. It also can't feel too thin or watery so as to seem cheap. In addition to these flow properties, the product must also have a carefully controlled pH range so that it's not irritating to my skin. So as a polymer scientist or formulation chemist, how can I achieve these complex properties desired by our customers? Well, the properties I described for this product are roughly those of a special category of fluid called a yield stress fluid, which behaves like a solid at rest and flows like a liquid when stressed. This means that when properly engineered, a yield stress fluid should stay in the container when not disturbed, but still flow and spread over your skin when being stressed by your hands. Many common personal care products and food products can be categorized as yield stress fluids, including those shown here. We have peanut butter, toothpaste, hand lotion, and hand sanitizer. The behavior is characterized using a rheometer to measure what's called the flow curve, shown here in the bottom left. In this measurement, the fluid is placed between two surfaces and sheared at a controlled rate. The shear stress required to reach the specific shear rate is then recorded by the instrument. The shear rate is scanned over a wide range, which produces the so-called flow curve depicted here, where we have the shear stress shown on the y-axis and the shear rate shown on the x-axis. This characteristic behavior of a yield stress fluid is that as the shear rate slows down to zero or approaches zero, the shear stress reaches a plateau value here on the log-log plot. And this is the so-called yield stress of the fluid. This yield stress specifies how much force must be applied to the fluid before it starts to flow. And it's critically important for achieving the desirable flow properties I described before. We'll see later how the viscosity is also calculated from this curve and how changing the formulation recipe alters the flow curve characteristics. For many of you in the audience, this kind of problem might seem familiar, even if you're not specifically in the yield stress fluid business. You might be working at a well-established traditional specialty chemical or chemical products company, and as an R&D leader, you might keep hearing how great machine learning and data science is and how it can accelerate innovation and drive business growth. You've perhaps read about its potential from other vendors or read about exciting results in academic papers. However, you're not working at a digital-first company. There are cultural and organizational barriers to change and simply the momentum of the historical way of doing things. You're still trying to figure out how to leverage digital technologies in your lab to grow your business, or maybe you're still not sure how to even begin. So today I'm going to walk through an end-to-end example tackling this personal care product formulation problem, going from a collection of historical spreadsheet data to a working machine learning-based decision support tool. And this example largely follows common things we've seen from working on similar problems over the last 2 decades. The first important step in the data-driven product development process is preparing historical data for machine learning. So let's first take a look at where the data comes from. Understanding the data generation pipeline is critical for designing a data-driven process that integrates with the operational realities of the lab. In this example, our base polymer is synthesized in the lab and then combined with other ingredients to make a candidate formulation. The candidate formulation then undergoes rheological characterization, thermal analysis, and other things. In this example today, I'm really only going to focus on steps 2 and 3 here, which is the formulation and rheology part. But you can imagine in more realistic examples, the process and the number of steps are many more. But the concepts I'm going to show you today can easily scale to more involved problems. So one of the important realities is that lab data has been historically analyzed, gathered, and reported using a very manual process. Raw data is copied and transferred from instruments to personal workstations using USB drives, and in some cases, results are first recorded in a paper lab notebook. In many cases, the digested data is entered into a template spreadsheet that's acted as a report to lab managers and used to help make product development decisions. However, these Excel spreadsheet templates vary in structure over time, and some scientists have modified them for their own purposes. In this kind of situation, you can technically find most of these historical spreadsheet files on a network share drive somewhere, but it's very difficult to find the results from old spreadsheets that you are interested in. So in practice, these historical data files are almost never used to help design new products and exist primarily as a paper trail for IP protection purposes. The situation I described here is the problem of what we call dark data. Researchers cannot see the data that already exists within their own lab. To shed light on this dark data, work must first be done to reveal the potentially useful files that already exist in various locations. With those files, those data files collected, organizations must then use tools to look inside the files and organize the detailed data to enable deep search, secondary analysis, and machine learning. One of the biggest challenges in shedding light on your dark data is that scientific R&D data is different from typical business use cases for data science and machine learning. R&D data has a different anatomy, life cycle, and set of use cases that differentiates it from other common forms of data like operations or sales data. R&D data has a different anatomy. It's more complex. In R&D settings, what constitutes data is often a collection of tables, images, videos, spectra, curves, etc. R&D data does not simply conform to a simple format like a table or a series of images. In addition, the anatomy of the R&D data for each laboratory is constantly evolving since the use cases are frequently changing and researchers are always in the process of learning which metrics are most informative. R&D data also has a different life cycle. It's expensive and slow to generate, but can be reused for a long time if appropriate context is captured. The laws of physics and chemistry are not changing anytime soon, right? But finally, the use cases of R&D data are different. In sales or operations, large amounts of data is produced as a byproduct of running the process and then can be used to help improve the process itself. However, in R&D, the main product is knowledge and data itself. The data is relatively scarce, and the design spaces are enormous. This presents a different kind of problem where the data itself is the limiting factor, and so we need to treat R&D data differently. So once labs have found some of their valuable historical data files, organizing the data inside those files requires deciding on a way to structure that data. This is done using a data model. Given the complex anatomy of R&D data and the different use cases for it, it's critical that domain experts drive this data organization process and do not leave this responsibility to their IT department. Domain experts in the lab are uniquely able to answer questions that are needed to get value from the eventual data systems you'll create, such as what data is important to include in the model. For example, what additional contextual information is needed to later understand what the data even means. They can also answer important questions such as how should the data be organized so that it's useful. The eventual data system must integrate to how the lab operates, how data is generated and used to solve problems. So here I have an example of the yield stress fluid formulation summary spreadsheet that the lab's been generating. So we have many of these files, and in here you can see a look at what this file looks like. You can see it contains some metadata about the experiment that was performed, as well as some recipe and processing data. It also may contain some intermediate characterization results here. You can see there's a pH measurement being done during mixing of the formulation. So that's one type of data that we've been generating in this lab. The second one is the example of a rheology summary spreadsheet, which also contains some experiment metadata and the resulting properties. And you can see these files already contain property data extracted from analysis of the rheology flow curve I introduced to you before. For example, you can see already here in the third to last cell here, or third to last row, you can see the yield stress is reported here. So that's already been extracted from the raw rheology measurements. And let's say we have tens or hundreds of these formulation and rheology spreadsheets that we've gathered over months or years in our lab. So how can we develop a data model to organize the data within them and then parse these files to the data and parse the data to save it and save that into a centralized database for using it for machine learning? Excuse me. So here we are. So how we did this to get our data organized, we used the Entha Edge Data Ops software tool shown here. The first thing we did was create data models to capture the data present in each of the summary spreadsheet templates. So here you can see I have the formulation data model where I've created entries for each of the types of data that are in that spreadsheet I showed you, and put them into category nodes. So you can see here I have category nodes. That forms a tree-like structure. This makes it easy to see immediately what pieces of information are metadata, which are recipe data, which are process parameters, which are property data. So this is a very nice, easy way to organize our data. And so we've done that for the formulation spreadsheet, and I've done something very similar for the rheology spreadsheet. So here the data from the spreadsheet is organized into similar categories, but we also have a new category here where we're going to be storing raw data from our rheology files later, and I'll show this later. Now, one of the great things about this data model building tool is that no programming is needed, no programming experience is needed to generate initial data models and get started. The tool is designed with the dynamic needs of R&D data in mind and allows researchers to modify these data models as needed. So as you learn what new things you need to measure, these can evolve with you. So with these data models in hand, we ingested data from over 70 formulation spreadsheets and 70 rheology spreadsheets into this database. And then with that information now stored in our database, we have the ability to run deep search on this data. So with this tool, we can build complex searches that combine information from multiple data models. For example, here we can combine formulation information with rheology information. We can look for historical formulations we've made that have particular yield stress or viscosity properties. And we can visualize our historical data here on the bottom using this Visual Data Explorer. For example, we can say, well, what's interesting here? There's sometime in the past we made a formulation that has a yield stress of 200. I want to learn more about what that formulation is. What did we do there? So you can select this and it highlights this entry, this row in your table, and then you can go in and explore further all of the data that you have about that particular formulation. So even before we get to machine learning, having deep search capabilities over my historical data can provide significant benefits to learn from what was done before and use this information when planning out a new series of experiments. Okay. So back to our data-driven product development plan. All right, we have our data organized, and now we'd like to start doing machine learning. But wait, do we have high-quality data? With these kinds of small data problems that we're dealing with here, high data quality is essential. And we just imported a bunch of spreadsheet data. We don't really know if that's good data in there yet. So let's take a few minutes and talk about data quality in one big way that we've experienced to improve data quality. One of the biggest challenges is that when you're importing historical summary spreadsheet data is that many of the important properties are often derived from human-driven data analysis, procedures that are not well controlled. Over the months and the years, different researchers have been performing the raw data analysis differently, handling outliers and artifacts differently, setting up peak finding or curve fitting differently. These differences have propagated to variability in the property data. And we have no way of auditing these differences where they come from. And so when we ingest a bunch of summary spreadsheets, there may be information there, but there's also a high degree of variability that can be present. So whenever possible, it's also important to collect raw data files and develop analysis scripts to unify how raw data analysis is performed across all samples. You may not be able to find all of your raw data, but what you can find, you can get started with, and you can set up systems so that all new measurements that you do in the lab are analyzed in the same way, or at least in a way that you can audit. This will significantly reduce the variability of both historical data and new data, and it also helps automate the analysis of new measurement data and dramatically accelerate new data generation to feed this new data-driven way of doing research. So now I'm going to show you, again, how we did this raw data analysis for this particular problem where we wanted to develop scripts to analyze the flow curve rheology data that's being generated by our rheometer. So let me share my screen again. All right, so here I have a Jupyter notebook. I know many of you will not be familiar with Python programming or Jupyter notebooks, but I'm going to walk through this and give you sort of a feel for what this is like to try to make you understand how accessible these things actually are. I would say most of what I'm showing you here in this notebook is definitely doable by an intermediate or even beginner level programmer. These are skills that every scientist can definitely learn in a reasonable amount of time. And so I'm going to walk through sort of the outline of what I'm going to show here. First, I'm going to show loading a raw rheology data file. I'm going to do some reformatting and cleaning of that data. I'll analyze the flow curve data. I'll calculate the viscosity. And then I'll use what I've developed in those first few steps to generate reusable analysis code, and then save all of that data into a database. I'll then calculate and save viscosity from historical data fit results, and we'll check our database. Again, we'll check our nth edge database to see that we have new data there and that it's actually interactive between what we're doing here on this notebook and what's saved in our centralized data storage system. So first, let's load the raw rheology file data. Here, I'm going to import a package that handles files. I'm going to import a tabular data manipulation package called pandas, which is very common and very powerful and allows you to do a lot of tabular functions that you might do already in Excel or other spreadsheet-based systems. We simply apply a file path. We supply the file path to a particular flow curve coming off of our instrument. And then in this particular file, we have two sheets in our spreadsheet. We have a flow sweep sheet, which is the raw data from the flow curve that's generated by the rheometer. And we have a detail sheet, which is basically a large metadata sheet about what we've done. And so, for example, you can see here, I printed out the first segment of the detail sheet, and you can see this particular instrument here generates a bunch of information about, who did the measurement, what day it was, some serial numbers and information about the instrument. These are all pieces of information that you can extract if you want to save that in your database with each measurement. Now, for a rheologist, right, the more interesting data is the measurement data itself. And so in this particular case, this is essentially a tabular view of that raw data that's generated by the instrument. We have columns here. We have the shear stress here. We have the shear rate. We have the viscosity. Then we have some other things like step time. That's the time between different measurements. We have the temperature being monitored over time. And then we have the sort of the normal stress, or the stress of the plates pushing down on each other. This is all generated by the instrument. And the data I'm interested in for extracting out things like yield stress is this shear stress and this shear rate. So let's do some manipulation to get this data ready for doing analysis. So we'll do some basic reformatting and cleaning. I'm extracting out this first row here, which contains the units of the data, to get that out so that all my columns will be only numeric moving forward. I can do some unit conversions to get things in the desired format. And I can do some very simple high-level filtering, removing invalid or unphysical data. For example, the shear stress can't be negative, so I can remove that. The shear rate, I can set some threshold value here to sort of filter down data and come up with a data set that I feel confident that's going to be a good flow curve. So this is my, after some light editing, this is my raw data. I can then analyze that raw data, and I want to import here some very popular packages such as Plotly for creating interactive plots, and NumPy for doing array math. And so in this problem with the yield stress fluid, this is analyzed often using what's called the Herschel-Bulkley yield stress fluid model. So the Herschel-Bulkley equation is shown here, where the shear stress equals the yield stress plus a constant k times the shear rate to the n power. So you can see that I have yield stress, this k called the consistency index, and this n called the flow behavior index. And these other k and n's aren't super important for the design problem we have today, but they're of interest, and you can extract them from a fit. So the idea is you want to fit this equation to your flow curve data. And I can very simply translate this mathematical form into a Python function here with just a couple lines of code. And I can then generate, using the plotting tools, an example of what does this function look like. And so here I've plotted, using a few lines of code, a hypothetical flow curve. And this is the same curve I showed you on the slides a while back. So you can see there's this sort of plateau value here at 100, and then it curves upward as we go to higher shear rates. This is what a Herschel-Bulkley equation and a Herschel-Bulkley flow curve would look like. Right? However, real data is not perfect. There's going to be noise, there may be artifacts. Let's see how we apply this function and how we fit real experimental data that we've extracted from that file. And so to do this, we can use a library called SciPy, which contains lots of really great scientific tools in there. And we're going to use a function from their optimized package called curvefit. By default, the curvefit function performs a least squares fitting of your function to your data. So a very standard fitting methodology. And so we can do this, right? A couple lines of code, we feed in our data, we feed in our function with some initial guesses for our fit coefficients, and we get it, and we can plot the results of our fit. And so you can see here the blue dots is our raw data from that file, and then the red line here is the fit. You say maybe that's pretty good, but you'll notice here there's sort of this curved shape here, but then there's something kind of strange happening here at low shear rates, where there's sort of a second dip here at low shear rates. And this is actually likely to be an artifact. And we've seen this in quite a few of our files, amongst other small artifacts that you can see. And so the question is, if we were doing this manually, right, we could sort of cut this off and say, let's only fit out to 0.01. And so we'll get a fit, and we'll sort of disregard this data at the lowest shear rate. However, this isn't always there, and the shape and the nature of this will change. Where the onset is may shift. And so we want to find a way of doing this programmatically so that a person doesn't have to sit there and supervise this fitting process for every single measurement that we're doing in the lab. So as it turns out, there are better ways of doing fitting than standard least squares methods, ones which are more robust to outliers and artifacts in your data. For example, the curvefit function that comes with SciPy Optimize has other options that you can pass into it, which allows you to use a curve fitting method which is much more robust to outliers. In this case, I'm using this TRF method with the soft L1. Like, you don't have to know all these details. There's really extensive documentation there that'll help you learn how these tools are used and when to apply them. And you can see I've applied this. I've refit my data using this new method, and I've now plotted and overlaid the two curves on the raw data. And you can see here, my robust fit shown in green looks much better. it sort of automatically detects that these data points down here are sort of the outliers, and it ignores that. And so with that in mind, I can then come up with a much better fit to my data. From this curve, I can also calculate the viscosity here. And so the viscosity, because this is a shear thinning fluid, decays over time. The viscosity is calculated as the shear rate divided by the shear stress divided by the shear rate. And I can utilize those fit parameters to calculate the viscosity at a given shear rate. And in this case, I'm using what's called the application viscosity, which is a benchmark viscosity measured at 10 inverse seconds. So I can take this code that I've shown you above, and I'm not going to show all the details, but I've essentially wrapped all of those steps I've shown you into functions. And then I can apply these functions to any arbitrary raw data file that I have in my collection. I have 50, 100 data files, and I can simply go through and apply them. And that's exactly what I've done here. I've applied that code again and again to all of my data files. I've extracted out the fit parameters, and then I save that information back to our database. And so I'm going to skip ahead a little bit, but you can see I've basically built a simple loop where I'm extracting out the measurement data and the summary data from the file, and then I'm using these methods to connect to my database and save it. And you can see here, I'm going through all of these measurement files one by one, extracting the data, analyzing them all the exact same way, so that I can be certain about where the results are coming from and making sure that the results are consistent. So that concludes the how we did our raw data analysis. So if we jump back now to this thing, we can now say, okay, yes, we've improved our data quality, and we're ready to move on to the machine learning part of our process. And before we jump into some of the machine learning details, it's important to remember why we are using this digital technology tool. It's really all about making better decisions that are informed by our historical data and backed up by statistics. So how do we do that? So for this problem, we're going to start by developing a machine learning model that can predict our properties of interest. This would be the yield stress and the application viscosity. Then we want to use those predictive models within a recommendation algorithm that will also take into account our design objectives and constraints and recommend which experiments to perform next to efficiently meet our objectives. And finally, with these two pieces in hand, we want to deploy them into an iterative optimization loop where lab researchers work closely together with all of the digital tools we've created here to accelerate yield stress fluid formulation optimization. So I'll show you at a mid to high level how to do this. And let me share my screen again. All right, so we're jumping back into the Jupyter Notebook environment. And I'm showing a separate notebook here showing this data-driven product development step. How do we do the machine learning? How do we leverage machine learning tools and technologies for product development? So I'm going to go through a series of steps. First, we're going to set quantitative design objectives. We're going to do some exploratory data analysis. We're going to develop machine learning models, 2 of them, one for yield stress, one for viscosity. We're then going to develop the recommendation system, and we're going to demonstrate how this is deployed and how we do formulation optimization with this adaptive experimental design methodology. So first, I'm going to show some of the concepts at a fairly high level. I'm not going to show too much code due to time, but if you have questions about any of these things at the end, feel free to ask, and I'd be happy to show this a little bit further in further detail. So first, let's define our design space, right? We've set some rough constraints on our space. We're going to vary the amount of polymer in our formulation. We can vary the acidity or the pH of our formulation. We can also vary the amount of salt. For this initial example, I'm going to hold salt at 0. So the range of my design space for salt is just 0 because it makes it easier. It converts this into a 2-dimensional problem, which makes it easier to visualize and show to you in this demonstration how these tools are deployed. But it's fairly trivial to expand this, to add the salt dimension or other dimensions in the future, as many real problems that you're dealing with in the lab have many more knobs to play with in the lab. But this can be extended fairly straightforwardly. Then I'm going to define some initial design targets. If my design target, I want to create a product that has 15,000 centipoise for my viscosity and a yield stress of 100 pascals. let's just set those initial design objectives. I can then again plot my design space. So I can plot the yield stress here on the y-axis and the application viscosity on the x-axis. And this gives me a feel of where all of the previous formulations we've made in the lab sit within our design space, within what we've done in the past. And so I can see here the target that I've set already sits right here. So it's sort of an interpolation within region of property space that I've accessed historically. If I wanted to set my design targets to be far away from where I've already measured in the past, this would be a much more risky endeavor, because there's always a chance that within the bounds of the design space that I have, I'm not going to actually be able to make a product which has those particular properties. And so you can, even before you get to machine learning, you can visualize this and make sure you're setting up a fairly realistic design objective. If you're trying to venture further outside of property space from where you've measured and made things in the past, you're likely to, this is going to be likely to be more exploratory and require a longer time frame to try different ingredients, to try different chemistries. However, if you're doing sort of a more minor tweak to a reformulation problem, and you target a product within a regime where you feel fairly confident you can access, you're much more likely to be successful in a rapid time scale. So with this design product in mind, let's do a quick exploratory data analysis of our historical data here. I'm plotting now the viscosity as a function of the amount of polymer in our formulation and the acidity. You can see roughly we have this sort of power law shape here, particularly varying the polymer concentration in our solution has a strong impact on the application viscosity, as you would expect. But you can see here a fairly small change in polymer amount has a fairly large impact on viscosity. You're looking at over an order of magnitude change in viscosity over this range here. And so when we identify things like this, and we expect things to be there, maybe from our physical knowledge of how polymer concentration relates to viscosity, we can transform our data. Much like you would do for doing sort of a physics analysis, you can take transformations of your data. In this case, I'm taking a natural logarithm of the viscosity and the natural logarithm of the polymer amount. So there are many cases where plotting things on a log-log axis will linearize the phenomena. And if you have a very specific physical model you're trying to fit to, this can be very helpful. But even in machine learning, where you don't have a very specific model, you want to fit a very free-form, non-parametric model, doing things like log transforms can help linearize your data. And it doesn't have to be perfectly linear, but doing these kinds of transformations can make it easier to fit a machine learning model to your data. So this is something we've been able to identify just by looking at our data here. We've identified a helpful transformation. And so we're going to see how that carries through into the machine learning model that I developed. So next, I want to show how we develop a machine learning model for this problem. Machine learning model development, regardless of the problem you're working on, roughly breaks down into a few steps that are very common. First, we want to split our data set into training and testing subsets. We want to develop a machine learning regression model pipeline. We then are going to perform hyperparameter optimization. Then we'll inspect and score the best models from our optimization. And we're going to finally, once we've selected a model that's the best, we're going to train that model, or the models in this case, on all of the data that we have and save them for later use. So let's go through briefly what this looks like. I'm not going to show and discuss all of the specific lines of code, but I want to give you a feel for what it looks like to develop a machine learning model for this type of problem. And so here, there's only a few lines of code can be written to sort of extract and split up our big data set into a test set and a training set. And you can see here our training set has 31 observations. That's 31 formulations we've made. And 8 of them are going to be left aside and kept as a testing set. If we're developing a good model, the model trained on these 31 should do a very good job at predicting the performance of the left out 8 set of measurements. And this is how you determine that your model is good. It's a little bit more complicated than that when you get into it, but this is the gist of the concept of training and testing subsets. So what I'm doing here and what I've done is develop this machine learning pipeline using very common, well-documented open source tools. In this case, I'm using scikit-learn primarily, and I'm also using some tools from a library called GPy, which implements a Gaussian process regression. These tools are well documented, and there's a lot of resources online that can help you get started. You can build very powerful models, very powerful systems using common open source tools if you know how to apply them and you know the types of problems that work well to be tackled using these tools like I'm showing you here today. And so a machine learning model pipeline is fairly simple. So here this is essentially a machine learning model pipeline I've developed. It has 3 stages. First is a transformer, then we have a scalar, and then we have a regressor. The transform is simply performing that log transform I showed you above, where we're taking the log of the polymer amount, and we're taking the log, and then we're going to eventually then take the log of the output as well. So we're going to take the log of the viscosity and the log of the yield stress. So you can see with just a few lines of code here, we've built a machine learning model that sort of uses this data that we've visualized in our exploratory data analysis and create predictions. We'll then set our model scoring metric, skipping past the hyperparameter optimization step. But in the end, we end up with a model that looks like this, right? So all of the dark gray data, this is the data from our training set. And this surface plot here shows the data fit to that at 0 salt. And then the pink data points here are our test set. So these are pieces of data that are not included when we fit our model. And so we hope that the ultimate model will predict their values fairly well, and it does. The main outlier being this slice here, which is the salt data. So if you kind of ignore that slice, we've developed a pretty accurate model for our data for the viscosity, and then similarly for the yield stress, which I'll skip for time. But in the end, we've done our model scoring here, and we produced 2 models, one that can predict the viscosity within about 25% accuracy, and one that can predict the yield stress within about 25% accuracy. And these models, while not perfect, are still very useful for us when we want to leverage them for a recommendation algorithm. So we train our final models, and we can visualize it. So this is now the final model. This is now the final model trained on all the data. We don't leave any data out. So let's utilize those final models and develop our recommendation system. So the recommendation system is built by first generating model predictions over the design space. We then calculate an objective function. We calculate the acquisition function. And then from that acquisition function, we generate our recommendations. So what I've done here is I've loaded in these trained models, and I've calculated their predictions over our design space. I've then defined a series of functions here. One which converts our multi-objectives. So we have 2 objectives that we're reaching. We're looking for a specific value of viscosity and yield stress, and I've combined these into a single objective using the weighted sum method. I then pass that on to a function called calculate EI, which is called the expected improvement, which is a very common algorithm to be used for the acquisition function. And essentially, this acquisition function is going to be what determines where you measure next. And the expected improvement algorithm balances your desire to go for the answer with the uncertainty that you have, because there are regions of parameter space where you don't have a lot of data and the model is uncertain about what the value will be there. And the expected improvement balances these 2 things and gives you the ability to be more greedy or to be more exploratory in your experiments and in the plan that you set forth for optimizing your formulation. So again, I pass my data into these functions. I calculate the expected improvement over my design space. And then I can get my recommendations from that particular acquisition function. And so I'm plotting here what this looks like. So here again, this is on the left is our fit, and on the right is our acquisition function. So I'm showing the expected improvement here on the vertical axis over our design space. And you can see here that there's a peak here, which is saying, this is where I recommend you measure next. And if we were only getting one recommendation for one experiment, this is what you would get. However, we've modulated and we've tuned this algorithm to be integrated with the realities of our lab. In this particular case, our collaborators told us we prefer to do 4 measurements at a time, because that's how our lab works. It's more efficient. And so we've actually tuned this to provide 4 recommendations. And so you can see the first recommendation here There's a second recommendation here in red diamond, the third recommendations in the purple diamond, and the third and the fourth is here. So we can see we're not just recommending one measurement, we're recommending a series of measurements which sort of span a much narrower range of our parameter space and designed to give us maximal information to help us reach our design objectives. So with these recommendations, we can then go forward and we can say, and we did this, we gave these recommendations to our collaborators. We said, our algorithm is recommending that you make new formulations and test them here. And that's exactly what they did. They made new measurements here in the red circles. We added in the data. We utilized our automated data analysis of the raw data files. We utilized our nthought edge database system, and we then were able to retrain the models. And so as you go through this iterative step, updating your models, generating new data, you're gonna rapidly narrow down on the parameter space of interest to find the material that meets your design specifications. And this is going to be much faster than just doing a trial and error, sort of a grid space search or traditional design of experiments, because you're leveraging all of the historical data you have. And as you learn information, your plan is improved and changes over time. And this is really the gist of how this adaptive experimental design or this data-driven optimization works. Okay, so with this in mind, to conclude, domain experts can and should take ownership over their data organization to ensure that these systems evolve and deliver value to solve the problems they have in the lab. You can go from scattered historical spreadsheets, which I had, to powerful and valuable decision support tools in weeks and months. These tools can help researchers meet complex design objectives and narrow down their search over a giant parameter space. These tools are particularly powerful for tackling formulation optimization problems. The final thing I'll say is, you can do this in your lab, and you should do this in your lab. And if you're interested, we can help you get started. So with that in mind, I'll leave it open for questions. I'm leaving here the contact information for Chris and myself. Feel free to reach out to us, and we're happy to answer any questions that you have. Yeah, the floor is open.
Thanks, Mike.
Okay. Oh, great. Well, we had some questions that came in during your guys' presentations. Let's start with this one here. Somebody asked, what courses do you recommend to take for being able to program and model?
Yeah, I guess I can take that one. There's various courses out there on machine learning. I would cover part of that. We provide some ourselves. In terms of diving deep into a problem like we did here, a more immersive experience might be useful. So we ourselves at nthought have an applied computing program where you can sign up, bring a problem, go through some courses, and then we help you through things like this. So there's various ways to do it through publicly available courses or through companies who provide training. Machine learning is a good place to start, and scientists knowing what they want to achieve and knowing how to translate from the science to the machine learning, as Mike's done here, that helps you get there.
Another question that came in asks, how do you decide which samples to collect data? So, for example, you could have sample 1 viscosity equals 1, the temperature equals 100, and sample 2 has a viscosity of 2 and a temperature of 200, etc. How do you decide which samples to run and how many samples?
Yeah, I'll take this one. So that's kind of the purpose of the recommendation algorithm, is to recommend to you samples that, based on your historical data, based on your models, based on statistical analysis, these measurements are going to be most informative. That being said, they are recommendations. If you strongly disagree with a recommendation as a scientist, you have reasons, you can disregard that and perform, and maybe you kick one out, especially in the case where it's recommending something which is not physical, or like the algorithm only knows what the data knows. You as an expert know more, from your experience things. But largely, you'd like to try to follow the guidance of the algorithm to some degree, because it's really designed not just to meet your objective, but to reduce the uncertainty in the predictions. And so in an ideal case, once you feel comfortable with the recommendations it's giving you, you would largely follow the recommendations, perform the measurements, and then add data. And the recommendations in the model are going to improve every time you make a new measurement and add new data. The model is getting better. It's learning as you gather more data.
Another question that came in asks, what if the format of an experimenter's e-notebook is not the same as another experimenter's? How do you get that information into your model building tool?
Yeah. I'll take that one just because I had a conversation about it yesterday. The tool that we've shown allows you to ingest data in different formats into the same models. So you need the flexibility to do that. It's important to note, though, that flexibility is needed at different times. Early on, the translation of notebooks and different ideas of what the experiment is and the data you need, that should be flexible early on, and you need a tool that can help you be flexible. Once everybody's kind of understanding the needs of the data and largely agreeing, that's the time to instill some data governance, trying to get people to conform maybe a little bit. But that flexibility is still needed afterwards, because research is agile, and the tools that you need for this should also be agile. But specifically to your questions, the tool that Mike showed just a little bit of can handle that. If you're looking at tools for this, from our experience, the flexibility, however, is to change that is very important.
Another question asks, how many models are available that can be used in machine learning?
So just to sort of clarify, I mean, you asked how many models. Well, the model is the individual thing you build, so there's infinite. But maybe more to the root of it, how many types of models, right? Because I use a particular type of regression model. I use what was called a Gaussian process regression model method. There are many, many more. But the reason why Gaussian process regression is extremely popular for this kind of problem that I'm showing you is that it not only generates a prediction, but it generates an uncertainty of that prediction. And so you can leverage, like in science, uncertainty of predictions is critical. The data you gather has uncertainty. You can propagate that through to prediction uncertainty. But you can leverage this uncertainty to help make better decisions. And that's what the recommendation algorithm is picking up on. It's saying, where do you think the best measurement is, but also how certain are you in that value? And there may be different regions of parameter space. There may be multiple solutions, and the model has different degrees of certainty about different parts. So that's really the benefit of the Gaussian process regression. There are a handful of other methods which also give you uncertainties, but many of them in sort of the traditional machine learning field don't. They just give you a prediction. Like a standard neural network just gives you a prediction. It doesn't give you uncertainty. And so for this kind of problem that we're dealing with, having that uncertainty is really powerful.
Okay, well, I want to say thanks, everybody, for submitting the questions. We're past the top of the hour, so that's all the time we have. Thank you, Dr. Hyber and Dr. Farrow and Dr. Spicer via video for your fascinating presentation. And thank you, participants, for being a great audience. Be sure to check CNN or CNN Online for information on the next edition of CNN webinars. Thank you, On24, for technology and production services. And thank you, nThought, for the sponsorship to make this interactive webcast possible. For CNN webinars, I'm Jeff Huber, and I hope everybody has a great day. Thanks.
Thanks, Jeff. Thanks, everyone.
Thanks all.